All right, Thomas Dimitrovich here. Welcome to another IAEI News Live. What we're going to do today is clean up a little bit of conversation from last week on transformers and talk a little bit more about some industry news that's happening, some resources that are available from IAEI, and a little bit about the upcoming section meetings, and it all starts now. All right. Okay, welcome back. I'm glad you can join us. Again, as I said earlier, this is a recorded session, so I apologize for not being live, but we just can't do it every single time. But we had some really good discussion last week on transformers, and I know I billed it as looking at the 112.5 kVA transformer and the 75 kVA transformer, and we spent the majority of the time going through the example for 75 kVA transformers. Now, we covered the fundamentals. We covered what you're going to need to understand to be able to what I tried to do was create fishermen. I tried to teach you how to fish so that you can go out and apply what we learned there to other transformers regardless of the size. Now, we may be using different tables. You might be using 450.3A instead of B. Maybe some of the details on the rules are a little bit different on the percentages based upon the size of the transformer or the full load amps, etc. But the fundamentals are all there. So if you didn't get a chance to watch those 3 sessions, I'd watch them in series. The first one, we went through some of the fundamentals. The second one, we talked about selective coordination, which really is an advanced topic. And the third one is a session on arc flash and incident energy. And throughout, we had really good engagement from viewers. So we answered and we fielded questions as we went. So what I'd like to do, though, is I'd like to talk a little bit about the 112.5 kVA transformer, because we didn't hit it. All right, so I want to clean that up, and then I have some industry news I want to talk to you about. Okay, so as we learned last week, 450.3B, because both the primary and the secondary of this transformer are less than 1,000 volts, we are in 450.3B. This one of the things I want you to understand is when you look at 450, Article 450 in the National Electrical Code, that article is focused on protecting the transformer. Short circuits, overloads, and you know, the conditions of use. We have new requirements in there to try to address people, you know, putting things on top of transformers. Ventilation is very important. So 450 is about the transformer. It's not about downstream panel boards. It's not about downstream conductors, upstream conductors. It is about the transformer. So as you look at the so what you'll recognize in this table, 450.3B and A for all that matters, we talk about the sizing of the primary and secondary overcurrent protective devices. We don't talk about sizing of the conductor for the feeder on the line side, or the transformer secondary conductor on the secondary side. We're talking about the primary and secondary overcurrent protective devices here as a percentage of the full load amps of the transformer. So the primary protection on a transformer, it gives you your short circuit protection, your high fault currents for faults either internal to that unit or external downstream of that unit that are very high available fault currents that will flow past through the device, through that transformer. Because remember, the transformer doesn't cease to do its job. Yes, it's a big iron core. There's no moving parts. In some cases, you have a different voltage on either side. In other cases, you might have the exact same voltage on both the primary and secondary. It's a 1-to-1 transformer. That is still a transformer, but it's serving a different purpose. So either giving you an isolation, or it's giving you reduced fault currents. There's a lot of different reasons that you might use a one-to-one transformer in an installation. Isolation, to establish isolating the whatever is on the secondary from the rest of the system is one reason. Another reason is to reduce the available fault currents for either equipment ratings, performance of overcurrent devices with regard to selective coordination, or other things like that. So be mindful that 450.3b tells us primary protection only, and you'll notice that when I'm using primary protection only, I'm at 125%. If I have primary and secondary protection, my primary overcurrent device can go up to 250%. Why is that? In the case of when I have a primary only protection, right? So let's do this. I have a transformer with primary and secondary protection. I have a transformer with primary protection only. In the case of when you have a primary overcurrent protect device and a secondary, this device here provides short circuit protection for that transformer. This device on the secondary provides overload protection for that transformer. Very similar to motor circuits. If you think about how we do the overload in a motor circuit, if you take a look back at 430, they'll tell you where the short circuit protection needs to be. But for the overload protection, your overload elements can be at different points in the system. Why is that? Before we get to a primary only protection, let's talk about what is that. What is the difference between an overload and a short circuit? The difference is that an overload stays in the circuit. So if I drew a circuit, and let's say I put a load down at the end, and I have a source. So V source, this is a conductor, C1, C2, and let's say that this is a light. It's a light. And, or how about a motor? Let's do a motor. I don't know why. I just like motors. So, because we're talking about a motor circuit, right? So, if I put an overcurrent device here that's providing short circuit protection for this circuit, I could put my overload protection here. I could put my overload protection down here. With regard to overloads stay in the circuit. An overload will stay in the circuit. A short circuit, if I have a short circuit in my system, say I break the circuit here, and now my current flows through the short circuit, but it doesn't go through the load. I've gone outside of the path of the circuit, the normal path. Overloads stay in the path of the circuit. Short circuits go outside of the path. So if I was going to try to say, how do I know the difference between an overload and a short circuit? A short circuit is when the current goes outside of the normal path. If I have a circuit with wire behind the wall and I have extension cords, if I add more loads to the circuit, all of the current is staying flowing where it's supposed to go, but I'm just pulling too much. That's an overload. If I damage my conductor and the current flows line to neutral, line to ground, line to a piece of equipment, it's going outside of where it's supposed to flow, and that is a short circuit. That will give you higher fault currents because you take the load out of the picture. So when I go and when I think about um, the two examples that we talked about with the primary only overcurrent protection, this primary device is doing all the work for short circuit and overload. If you look at the tables, this is 125% you can't exceed. When I give primary and secondary protection, this device can go up to 250%. Why is that? Because that primary device is not giving me overload protection. And if I drew a damage curve, for example, so if I had a time current characteristic curve and we went over this last week, go back and take a look at any one of the, I think the first session we do plot these curves. If I look at the time current characteristic curve, I have current down the bottom, time up the axis. I put my transformer damage curve up here. I have inrush. So this is my transformer damage curve. If I have my transformer damage curve, I want all of my overcurrent devices to clear in this area over here, and not this area over here that would provide damage. If I let high enough current persist long enough, I can damage my transformer. That would be ungood. So what we do is if I'm going to provide short circuit protection, primary overcurrent protective device, if your overcurrent protective device cuts into that transformer curve, that's okay. You might say this is not being protected, but it's actually going to be protected by this secondary overcurrent protective device, which will be plotted over this area here. So that's the fundamental thing you have to remember, is that Article 450 is thinking about what we just showed on that screen. It's thinking about the protection of the transformer in relation to the transformer damage curve, and which I'm going to make something else too. In the sessions last week, I plotted a typical transformer damage curve. I did not have the actual damage curve for that transformer. Quite frankly, it's going to be hard to get a damage curve for every single transformer. For a 112 or 75 kVA transformer, you're not going to get that information. You're just not going to get it. What we use are standard ANSI IEEE rules of thumb, or damage curves that have been developed based upon the standards, the IEEE standards. And you'll find those curves in transformer standards to say, look, this is your typical transformer damage curve. And remember, you're dealing with a big hunk of iron, and your protective devices give adequate protection as long as you could use these typical damage curves as opposed to actual damage curves for the device that you have, and that is getting you in the ballpark, and it's adequate to provide that, to demonstrate the protection. But keep in mind that as you get into larger transformers, very large kVA or MVA transformers, you are going to have a lot more information from the manufacturer for that transformer, a lot more than you would ever get for a 75 kVA transformer, and smaller. Remember, the smaller that you get, the less cost that you have. And if something happens to some of these really small transformers, it's more economical to simply replace them than to spend all of the money that you would need to spend to protect them to the nth degree. Because you'll probably spend more money in monitoring and more money in relaying and protection for that transformer than the transformer's worth. So the very large transformers will have a lot more protection. They have what we call differential protection. Okay, so some of these large transformers will you'll have, say, a transformer, you'll have CTs on the primary, you'll have CTs on the secondary. Off of those CTs, you'll come into a relay, and that relay will look at the amount of current going in and the amount of current going out, and we'll say this is I in and this is I out. I in has to equal I out. And if they don't, that means current is going somewhere else. And there's not much places for current to go when in between these two current transformers. This is differential protection. For very large transformers, we'll employ things like this, technologies like this. They'll put temperature sensors, and those temperature sensors will go into the relays. And in some cases, the relay trip curves can change based upon some of those temperatures. If the temperature of the transformer, or even motors, we do this a lot with motors, if the temperature of the transformer or the motor is rising, the time current curve of the relay, the protective device, will respond in accordance with that to adjust itself and provide a better level of protection. So there are things that we employ for large transformers that we don't employ for smaller transformers, like your 75s and your 112.5s. But keep that in mind. I think that is something that's important for us to understand, that you might see much more technology on a piece of equipment, whether it be a motor or a transformer or other items. It's typically driven by the cost of replacement. You want to catch a failure early so you might be able to fix it, as opposed to replace the entire device, which could be very expensive. So now the NEC doesn't cover that. They give you what a primary overcurrent device has to be set at and the secondary overcurrent device has to be set at. But when you employ these other technologies, you are exceeding those requirements and providing a much higher level of degree of protection, because you will trip for very low differences in currents and provide a very fast response very quickly at the first recognition of a problem. So, all right, so we had the primary and secondary 450.3b giving us our maximum numbers, and you'll notice that when you have like primary only protection at 125%, you're allowed to go the next higher. But if you're at 250% in your primary and secondary protection, you're not allowed to go to the next higher. Those little details will get you. They've gotten me in the past, and it takes other sets of eyes in some cases. Hopefully hopefully you catch little problems like that earlier rather than later. I mean, that's a whole nother topic of accuracy in your design phase, and the importance of getting the peer reviews for your designs and your conductor selections, your overcurrent protective device selections, your protection settings, etc. Because you want to catch problems before you get into the field and before you start buying equipment. The more you can get nailed down early, the better off you are. And I'm telling you, there are some people that don't do well with details, and they struggle. And those individuals, if you're in the right positions and you're picking solutions and you're doing designs, you've got to pay attention to the details. All right. Now so we said that the primary, when you have primary and secondary, the largest primary device you can go is 250%, and you have to go down, not up. The other thing that came up, so you know how we like to go, we'll say you can go up to the next higher and all that jazz, but you really have to protect a conductor at its ampacity. So you really, there's times when you can go up and there's times when you can't. You've got to make sure that you're doing that correctly. We also said in 240.6, anytime in the code, when it says a standard ampere rating of a circuit breaker or fuse for an overcurrent protected device, you don't go to the manufacturer and find out what they have in the catalog. You go to 240.6a. That is your standard ampere ratings for fuses. That is the table that tells you you go from 80 to 90 to 100, 110, 125, 150, 175. Like, for example, we go to 300 to 350. If I made an overcurrent device at 325, that wouldn't be a standard ampere rating because that is my rating. It's not a standard ampere rating. Anytime in the code where they say standard ampere rating, you got to go to 240.6. So don't forget that one too. What else? All right, inrush currents. So we talked about inrush currents, and this is the challenge. I mean, the inrush current is like lock rotor on a motor. When you look at a transformer, and you look at a motor, and you look at generators, you're dealing with fields, magnetic fields. You're dealing with a lot of iron, steel, plates, all that jazz. And when you energize these components, in the case of a motor, you need to overcome the force to get the rotor moving, whether it is driving something that has locked rotor, whatnot. In a transformer, it's the energization, it's the magnetization or the flux, the fields that have to flow, and you are creating those fields to get that thing to do what it's supposed to do, which is convert your energy from primary to secondary. And there are inrush currents. You have energization inrush currents, you have recovery inrush currents, and you have sympathetic inrush currents. The energization inrush current is going to be your maximum current that you'll see flow. And quite frankly, if you have a transformer that you energize it and it trips your primary overcurrent protected device, if that was the first time you ever energized that transformer, that will be the worst case inrush currents. The second and remainder of the times you energize that transformer, you're not overcoming the same issues. The same issues that you had. You are creating a magnetic field with iron that's already been saturated. I know that's probably a lot more than what you wanted to know, but the first time you energize a transformer, it will be the worst case. If you are just starting something up and you trip the overcurrent device the first time, the second time might actually hold. So don't start changing settings and going back to the drawing board until you do a little bit more analysis. All right, and the typical inrush current is 8 to 12 times. Now, talk to your manufacturer. Some manufacturers will give you data and tell you their number is less than the 12 times. And that can help you because the inrush current is what makes us move a larger overcurrent protective device on the primary than what you might feel comfortable with. Because the inrush current would be in the instantaneous region of the circuit breaker or in the current limiting region of the fuse. So that number is an important number. And if we assume it too high, then I may buy an overcurrent protected device that's too large. I'll buy an overcurrent protected device that is adequate, but it may not be the most cost-effective solution. So always check with your manufacturer of the transformer. They may tell you what their maximum number is that they will have for those specific types of transformer. And remember, you've got copper core, you got aluminum, you have a temperature rated, you have high efficiency transformer. You have K-factor transformers that deal with the harmonic currents. There's just so many different types of transformers and different applications that you might use one over another. And that's a lot of that is outside of the NEC requirements. But it's important to understand. And work with your manufacturer, please. Okay, so then we moved into 408.36. And we said, now remember, 450 is about protecting the transformer. If you're going to install a conductor on the secondary, or you're going to install a panel board, for example, on the secondary, or a switchboard, then, or whatever piece of equipment, then you have to go to appropriate articles within the NEC to understand what the requirements are for proper protection. And in 408.36, they tell you that if you are on the secondary of a transformer, in 408.36b, I believe it is, if you're on the secondary of a transformer, then you have to put the overcurrent protective device on the secondary of the transformer, not the primary, to provide the protection for the panel board. And that's only when you're, well, I mean, there are specific rules for when you're on the secondary of a transformer. So you have to keep in mind that when the panel board is on the second, now there are other rules for panel boards that would not apply because they may not be on the secondary of a transformer. A panel board could be fed from another panel board. So you can have some flexibility in rules within 408 when you're not being supplied by a transformer. But when you are, make sure you follow the rules. And in the case of 408.36b, the only exception points you back to 240. So you're bouncing around the code, right? So what's 240? 240 is overcurrent protection. And you get into the discussion in 240 with regard to tap conductors and transformer secondary conductors. And a transformer secondary conductor is very similar to a service, because you don't have overcurrent protection at the source, and you have a length of conductor. They put restrictions on that length of conductor because you don't have that primary protection at its source. You have it at the load side whenever you're terminating whatever the overcurrent device is that you're terminating onto. That's what's giving you your overload protection and your short circuit protection for that conductor that's behind it. So just you think about the challenges there. So there are requirements. So what do we do when we're not going to provide short circuit protection for a length of a conductor? We have to do certain things. So in 240 tells you that, okay, look, if you have a transformer and you have secondary conductors, you know that they're not protected at the source of that secondary conductor. So we're going to limit the length. We're going to put restrictions on where you can route it and what type of protection. Why is that? They're going to put a physical protection requirements in to make sure you don't damage that conductor. And that's what the transformer secondary, that's what we do in transformer secondary conductors. We try to provide the mechanical protection when we're not going to provide the electrical protection, so we put restrictions. So in 408.36, the panel board says, hey, look, if it's good enough for the goose, it's good enough for the gander. The conductor needs to be protected. And oh, by the way, in 240.21c1, they'll tell you that you don't have to have an overcurrent device on the secondary. You can have a primary only protection of a secondary conductor if you meet certain rules. And the panel board guys are saying, all right, you know what? If it's good enough to protect that conductor, then if you follow those same rules, then you will protect the panel board on the secondary. But those rules are pretty doggone restrictive. Delta-delta transformer, single phase application. So they give you the details. And if you're dealing with a standard 112.5 kVA transformer, delta Y ground, that does not meet 240.21c1. So 408.36 forces you to have that protection on the secondary of the transformer for the panel board. 240.21c1 is going to require you to land those transformer secondary conductors on an overcurrent protective device and not be protected by the primary, because in these applications you're not going to meet the requirements of C1. You're going to be into the 10-foot rule and other rules which will govern basically if you're outside or if you're in a supervised energy, supervised industrial, etc. So you got to follow those transformer secondary conductor rules in Article 240 and follow 408 for protection of the panel board that you're working on. So 240.21c, C1 is primary protection only. C2 limits you to 10 foot with other restrictions. C3 is 25 foot, but you're in an industrial installation. 4 is outside conductors. There's no limit on the outside conductors because you're outside. You're not going to burn a house down. Secondary conductors from a feeder tapped transformer, and then secondary conductors not over 25 feet long, which is C6. So there's rules around those secondary, and I'm telling you, a lot of engineers and others, again, I'm not going to just point at the engineers, although I think they're a big offender, we miss that. And I am an engineer and a past, I'm a recovering offender of this rule. And it took me actually, it was a while ago, a long time ago, where I did a design and I did not have secondary protection. I did 6 overcurrent protected devices I was following. I thought the 6 disconnect rule, all these other good things. And my mentor walked me through the National Electrical Code and helped me understand the errors of my ways. And at first, when you do something, especially, I was a young engineer at the time, but other people learn this later and they've done designs this way. And then you tell them that what they've been doing is wrong. It really, when you read the language, because you're bouncing around, you just saw it. We were in 450, and then we went from 450 to 408, and we went from 408 to 240. You're bouncing around the National Electrical Code, and I'm telling you, it takes a special mind to understand exactly what is going on. And you really have to read it multiple times. That's the value of this organization right here. I'm here to tell you, IAEI has helped me walk through the code. And I remember, the power of the IAEI is you and me. It's not like there is some omnipotent person who's sitting in Texas who is going to put hands on you and you're now going to know the code. The power of the IEI is going to the meetings and building relationships. Listen to the questions that are asked, and for those panels, those individuals who are on the stage answering questions. Even if it's not something that you deal with, listen to all of that dialogue. Make the connections, and when in doubt, pick up the phone. What you'll learn is the members of this organization are always going to be there for you. They love what they do. They love to understand the code. We're all on a journey to understand the code. And this is one of those areas where a lot of people make mistakes. So don't feel bad if you've made mistakes in the past and you just learned something new and you go, wow, correct your ways moving forward. That's what I say. So anyway, let's do this. Let's walk through, what time is it? Okay. Let's do this. 112.5 kVA transformer, right? There's the nameplate. I'm looking for some important information from this. What can I ascertain from this? I can ascertain that this is a delta Y ground, right? I can ascertain the kVA. I have the primary voltage, the secondary voltage. I know my impedance. I know this is air cooled. The class AA gives me air cooled. I have my insulation. I have that it's a three-phase transformer. I have my type, KT13C. That's going to mean something with regard to efficiencies and all that jazz based upon the manufacturer's information. I even have a schematic down here. This is right off the nameplate. If you have the luxury of having a nameplate, that's great. But a lot of times in the design phase, we don't have that. All right, so we grab our information. And we have to calculate the primary and secondary full load amps. And what's our equation for that? Remember, primary and secondary, it's your full load amps is the kVA divided by the square root of 3 divided by the kV of either the primary or the secondary. If you do the kV of the primary, that's the primary full load amps. If you do the kV of the secondary, that's the secondary full load amps. I'm telling you, you got do single phase transformers, do three phase transformers. What happens if, here's a question for you. What happens if your kVA is, I don't know, say it was 112.5 kVA slash, I don't know, 225 kVA. And there was a FA, AA, FA. And you go, well, what's the FA? Well, fans are added, right? And that tells me that when I run fans, I can actually put more load on that transformer. So now I have different full load amps. And I have to make sure that when I'm running off of whichever full load amps of that transformer, that I'm picking my overcurrent protective devices correctly based upon whether I have fans or not fans, and what parameters are impacted. Are the inrush currents impacted? Is the impedance of the transformer impacted? So those are other important aspects that you need to think about. All right, so in this case, the primary full load amps is 135.3 for a 112.5 kVA transformer. So here's our transformer, 112.5, 480, 208, 4.17% impedance. Primary full load amps 135.3, and we know based on the tables that I can go 250% of that as a maximum, but I can't go over that. My secondary full load amps is 312.3. I know I can go up to 125% of that, and I can go to the next larger. I have single phase equations. These are my equations for full load amps. I just gave you. And remember, this here, right here, if you do the math, square root of 3 over 3 equals 1 over the square root of 3. So just be mindful of that. All right, so my primary overcurrent protective device, OCPD1, can be sized at 250%. 2.5 times 135.3 is 338.25. So I can't go to the next higher, which would be a 350. I've got to go to the next one lower, which would be a 300. So the largest overcurrent device on the primary of this 112.5 kVA transformer is 300 amps. And this is the time current characteristic curve. So look at there's your transformer damage curve, right? And you'd say, holy cow, Tom, the transformer damage curve is to the left. So if I have these currents flowing, if I follow that up, if I have a current of that magnitude flowing, it's going to not trip until well past the damage of the transformer. But remember, the transformer is being protected in this region up here from the secondary overcurrent protective device, secondary main. The primary has to let that inrush current flow and provide short circuit protection for the windings. That's all your primary overcurrent device does. Now, I can get better protection of the transformer in this region, even from the primary overcurrent device, with that 300 amp circuit breaker, if I put an electronic trip unit, ETU. You'll see that on drawings, ETU next to a circuit breaker that tells you it has an electronic trip unit. And people ask me, why would I put an electronic trip unit in it? Because of this right here. I can provide better protection for my equipment. And quite frankly, much less expensive than trying to put differential relaying and all the other jazzy, snazzy things you got out there. You're putting one device on the primary that is providing not only additional protection via this knee, but you know what that does? And if you take a look at our third session last week, that helps reduce the incident energy on the secondary of that transformer. This was the difference between 16 calories and 2 calories. Okay, I can get my incident energy lower from a short time delay that lets the inrush currents flow, but only those inrush currents. Any current that is in that inrush range and it persists longer than what it should, then that device is going to take that out. Okay, so on the secondary, no, that's still a primary. Now, if I only did 125%, which is typically what you'll see engineers do, I calculate 134. When I am below the 250%, and if I do 125%, I don't have to say, well, can I go to the next higher? No, because I'm below 250%. It doesn't matter what you do. You're just using 1.25 as, I don't know, you're pulling it out of the air. So you use 1.25 times 135.32, you got 134. You can put a 150 amp breaker. You can try to put a 125 amp breaker in, but what's going to be your determining factor on how small you go is going to be whether or not your overcurrent protective device is going to trip on inrush. What's the instantaneous pickup value? So in this case, I think I did with 150. So this is your 150 amp circuit breaker. You are still clearing inrush, and that's at 12 times, so that's a high inrush, much higher than what I would actually see on a transformer. And look, this actually gives me better protection of my transformer damage curve because I'm bringing it down lower. And remember, if I only had one overcurrent protective device, I would be using 125%. And this is why, because I'm getting short circuit protection from this device, which is smaller, and I'm getting adequate overload protection for the windings of my transformer from one device. But remember, I can't do one device on the primary unless what? Delta, single phase, go back to 240, 21C. All right, so this is if I used a fuse. Again, this inrush current is going to be your nemesis when it comes to trying to make sure you don't trip that primary overcurrent protective device. And this is a 125 amp fuse. This is a 175 amp breaker. So I actually, if with a 125 amp fuse, smaller fuse, I'm getting pretty doggone to a good protection from the primary. Look at this. I got a much tighter curve. This band is very tight, very fast acting. But when you're in this region up here, this is your overload region. It's not fast acting. This is where you get the fast acting, and that's what's going to give you your short circuit protection, much less damage than, say, the circuit breaker. But look, you actually do a very good job of protecting the overload region with a 125 amp fuse. All right, so secondary overcurrent protective device. I can go up to 125%, and I'm allowed to go to the next higher. Now, this comes to 1.25 times 312 is 390 amps. I'm allowed to go to the next higher because of the tables in 450. So I can put a 400 amp panel board. In fact, I could come off of here and go to another 400 amp main. I could put multiple panel boards in parallel with each other on the secondary of that transformer. And you might say, well, Tom, you're going to exceed the kVA rating. But there is nothing in the code that says I'm not allowed to exceed the kVA rating of a transformer. Now, this is what my secondary overcurrent protective device, if I do a circuit breaker, this is my maximum, my 250%. Remember, 250% is well to the right of the damage curve, and this is a 400 amp circuit breaker. But you might say that now this second damage curve, I talked about this a little bit. The second damage curve is for unbalanced faults. What we would typically do with these transformers is only plot the one. So I am sort of confusing things a little bit, but I get good overload, in my opinion. I get adequate overload protection for this transformer because I have, I'm in this region here, but I feel comfortable, very low exposure, and that device is going to trip in enough time that you're not going to damage the transformer. But that's by the code. I mean, even if I didn't like that, I could not reject it based upon the National Electrical Code. I could reject it, say, I don't feel you're protecting the transformer well enough. Okay, well, that's your opinion. It's not a code-related issue. And if I have my PE stamp and I stamp this design, I could say, I believe that is adequate enough. It's my opinion. All right, so this is the electronic trip unit on the primary. And look, the electronic trip unit does a really good job. I mean, it gives me really good overload protection, even better than the overload protection from the secondary over 400 amp circuit breaker. That electronic trip unit is worth its weight in gold, in my opinion. It will limit the damage on a very expensive asset to your organization, to anybody's organization. All right, and then this is my breaker on the primary. It's a 175 amp circuit breaker with a 400 amp fuse on the secondary. And you'll notice how the fuse, this is a fast acting fuse, you could tell, because there's no time delay. Remember, a time delay fuse, if I got a 400 amp time delay fuse, it probably would have come down about the same. There would have been a little bit of a hump in there and then down, right? So, and maybe even out a little bit further. So remember, the time delay fuse, it's all about the shape of the fuse, typically in that region. There will be current limiting, but it's this region of the fuse that gives you that time delay, and that's typically to ride through motor inrush or transformer inrush type of application. So, but on the secondary, I don't have to, unless I'm serving motors, I don't have to worry about that. I chose a fast-acting fuse here, and as you can tell, a non-time delay fuse, and it really provides a lot of protection for that transformer. Now there's the remember I told you there's the shape of the curve. So there's a time delay fuse. The green one here is the primary fuse, and that is a 125 amp fuse. This fuse here is a 400 amp, but it's an RK1 time delay fuse. You can just tell by the shape of it that there's the slope in, sort of slopes in and then out. And it gives you a nice curve. So if you have motor inrush currents, this portion of the curve is not running into motor inrush currents that might be here, where the other, because of this slope, those motor inrush currents may trip that fuse. So I did it both ways just to show you that a 400 amp fuse is not a 400 amp fuse is not a 400 amp fuse, okay? And this is one manufacturer's trip curve of a 400 amp fuse. Same thing with circuit breakers. A circuit breaker is not a circuit breaker, is a circuit breaker, is a circuit breaker. Every manufacturer's trip curves will be a little bit different, and it's important, especially if you want to provide more protection, you want to do a detailed analysis. This is what we do. This is what we do. And there's just, again, a fuse and a fuse protection for that transformer. Very good protection for the transformer. So that's the transformer. So we went through the selection of the primary and secondary overcurrent protected devices, and then the conductors. You're going to pick the conductors based upon the ampacity. I'm not going to go through that. That's a 310 exercise. You have a raceway. You've got to think about the number of conductors in a raceway. If you have to do any adjustments of ampacity based upon temperature, etc. But you're going to pick the conductors and for your primary and secondary equipment, feeders and transformer secondary conductors. Okay, so I don't know why I just did that, but I did it and it didn't do anything, which is a good thing because then I would have a problem. All right, so what I do want to do, I want to talk about, remember I said about this organization, the IAEI. There are opportunities all around us. And one of those opportunities is the analysis of the analysis of the code changes. We're getting pre-orders for the analysis of code changes. So if you go to the IAEI's website, you can take advantage of pre-ordering the analysis of changes and get your book early and often because you're going to want to start reading on what are the significant changes coming out in the 2023 cycle. Remember, if you have a membership, if you don't have a membership, really consider this organization because they'll being an IAEI member, you're a part of the crew now. I mean, you have access to a lot of really good information and resources, and I'm telling you, it's a good spend of your money, especially if a young engineer, you want to understand the code, get involved with this organization. Go here to education and go to local events calendar and look at what's going on this month and next month in areas around you. Find a meeting around you and get to that meeting. I'll tell you, my first IAEI meeting, I didn't know a soul. I didn't know anybody there. All I knew was that, I'll tell you how, nobody told me what I'm telling you. What I knew was that there were individuals that I talked to that were very educated, and I was doing some things with, I was working with Code Making Panel 2. I wasn't on Code Making Panel 2, but I was sitting around the room and listening to the people talk. And when you hear some people talk, they're pretty doggone smart. You ask them who they are, and you start to learn more about them. And everybody had something in common. They would talk about IAEI meetings that they learned something at. And that's how I got turned on to the IAEI meetings. I think I was the Ohio chapter, was the first one. I was asked to do a presentation there. And I did a presentation at the Ohio IAEI chapter meeting. It was in Columbus, Ohio. And I'll tell you, the audience was spectacular. The questions were challenging. As the presenter, I'm like, wow, that's a really good question. And I realized more and more. And then at that meeting, I sat in the audience. And I listened to people, and I'm like, I don't know what he's talking about. He's rattling off numbers, 450 dot this, 420 dot that, 408 dot this. Oh, can't forget about 110.3 and 90.2. I'm like, where are these numbers? And somebody said, those are all sections in the code. And I'm like, well, how the heck does he remember all those? They live it and they breathe it on a daily basis. And there was a lot of information that I was not in need of at the time. But over the years, I realized that all that time paid off. And more so that I had the connections to ask the questions. So get out there, find a meeting close to you, and go to it. Shake hands. You're going to feel intimidated. You're going to feel alone. But you shouldn't. There are a lot of really good people that will welcome you. Tell them you have never been to one of these meetings before. Tell them you heard it from Thomas Dimitrovich. You heard it from IAEI News Live, that you need to be here and you want to learn. And these individuals will definitely help you. There's educational opportunities. Now, the other thing I want, and what I really want to tell you about are the section meetings. We're getting more. So registration is open at every one of these section meetings. You got the Northwest and Southwestern meetings. This is a joint meeting, and honestly, in my opinion, they should have been doing this for years. Those two, the Northwest and Southwest, that's your your California, your Oregons, your Alaska, all the ways up in that region over there, Spokane, Washington, and all that good stuff, or your different chapters. They're going to combine meeting, and it's absolutely awesome. And that's going to be in Spokane, Washington, September 11th. So put these in your calendar. September 11th through 15th in Spokane. September 18th through 21st. This is in Sioux Falls, the Western section. I'm going to be there, and I'll tell you, we have a kick-butt program. Our program is going to go through each of the code panels. We have all these different code panel members coming from all over the country. These individuals sit at the table and they make the language. They are a part of the arguments. They write articles. They are the experts in the industry, and they will be at other section meetings as well. So individuals like Chad Kennedy from Schneider Electric, like Tim McClintock from NEMA, Tom Moore, IAEI, a lot of IAEI people and members. Joseph Wages, I'm counting on Jody being there. Joseph is a world of knowledge and information. He puts the book together with all of the other IAEI code panel members. He does a lot for the organization. He will be there in person. We'll have IAEI represented. You get to see Rudy Garza, and experience his passion for making this organization a success. Rudy doesn't come from an electrical industry, but he comes from understanding how to make organizations successful, and we are on a journey with the IAEI that I am very excited about, looking forward down the road. We're going to have a lot of great things coming. So Western section in Sioux Falls, South Dakota, be there. Eastern section in Lancaster, it's like Kentucky, Lancaster, Pennsylvania, September 30th through October 2nd. I believe that's over a weekend. So they Friday, Saturday, Sunday bit, I believe. Canadian section in Waterloo, Ontario. So if you're Canadian and watching this, get over to this meeting in Waterloo, Ontario. It's worth it. September 23rd to 25th. You will see Rudy Garza there too. So he goes to all of these. I mean, you got to get there. Southern section meeting in Savannah, Georgia. I believe I'm going to be there as well. So I think I'm on the program in the Southern section. I'm doing some things for the Western section. I'm the education chair for the Western section, so pulling together the curriculum for the Western section. But I'll be on the program in the Southern section. I'll probably be at the Eastern section. Those are the three that I get to. So you got to get on, and I'm hopefully going to have a booth where we can go live from the section meetings. I'm going to be working on that. I'm getting better at it. I'm not a pro yet, but we're going to get there. So you've got to get out to the section meetings, and I'm telling you, those meetings are fantastic, absolutely awesome. You will, if you've never been to an IAEI meeting in the past, my advice is to be a sponge. Be careful. Listen. Talk to people offline. When I say be careful, I'm just saying, when I say be careful, what I mean is, you might have a lot of passion about the code, and you might think you're the sharpest knife in the drawer. But when you leave one of these meetings, you're going to realize that you're not the sharpest knife in the drawer. You're probably not even the sharpest spoon in the drawer, like I did, and others have, because you are in a world now of individuals who live and breathe this, and they love to engage, and they want to help you. But they will also recognize that if you are wrong, they're going to want to make sure you understand that you're wrong. And to some people, that can be very intimidating. So listen. If you've never been to an IAEI meeting, my advice, this is what I did. I watched in awe my first few meetings, at least. First few months of going to these meetings. I watched, I listened, I talked about what I knew about. I set up a booth from an Eaton perspective, and I had AFCIs and GFCIs over there, and I talked about what I knew about with regard to the product. But I was a sponge when I went into the room when we start talking code, because there's a lot of passion. You will hear people argue with each other at the microphones, have differences of opinion on interpretations of language. And these individuals sit on code panels, and they are inspectors, they are designers, they're installers, contractors. There's utility individuals there. So there's a very good breadth of individuals who go to these meetings, and I'm telling you, you got to get to a section meeting. It's addictive. You will fall in love with it. If you love to understand and learn, you will fall in love with any of these IAEI meetings. So get to them, enjoy, take get a business card together with your contact information that you can share with people. Bring something like that to these meetings and establish your network of experts. So that's my message to you. All right, so I believe it's been about an hour, and I really appreciate your time today. I again apologize for not being able to go live today. I'm at the American Society of Healthcare Engineers. I'm doing a presentation today, this afternoon actually, and I've got booth duty. I call it booth duty, and you can almost get that to a song. But I enjoy talking to healthcare professionals. They care about reliability. They care about reliable and maintenance and all that jazz. So we're talking about building safety into all phases of construction. That's what my talk is about tomorrow. It's building safety into the design phase, the construction phase, and the maintenance, continued the living building phase of the healthcare industry. And as you may or may not know this, but if you've ever been to a hospital, especially some of these hospitals around colleges, they are constantly changing and adapting to new demands placed upon the healthcare industry. And it's just an absolute, it's amazing to see how that industry changes over time and where it's going. So, and in my book, safety is the first priority to build into your designs. And that's what I'm talking about a little bit after this presentation, 3:15 to 4:15 here in Boston, Massachusetts at the convention center. In fact, we were here for the NFPA meeting, so I know where all the restaurants are and all the restaurants. So anyway, take care. Thank you for joining me. Take care. Stay safe. God bless. And please stay healthy. And we'll see you next week. See ya.